So we're very pleased to have Spencer here. He came all the way from Alberta just to give this talk. He does a lot of teaching for us in our Pipeline Integrity Institute. We really appreciate that. He's an expert in cathodic protection, teaches cathodic protection to AMPP now. NACE was better.
I know.
Why AMPP?
Why? Yeah.
Well, because they merged with the coding people, so they had to come up with a new acronym.
Anyway, he teaches at level 3 or level 2 cathodic protection?
I'm level 4 certified.
Level 4
which is the
certified.
highest level.
Yeah.
And I teach level 1.
Level 1. Right. Teaches it here at UBC, and today he's going to talk about cathodic protection case studies. And I'm quite excited because I haven't seen yet any case studies. So I hope to find some new information here.
Yes.
And with that, thank you very much,
Ted,
Spencer.
and thanks for having me. I hope you guys can hear us online. I'm going to echo Ed's excitement here because normally when I talk about cathodic protection, it's very basic and it's very entry level. So if you have not heard about cathodic protection today, anybody? Good, because this would go over your head. So I'm excited too. It's the first time I've gone more in depth into the cathodic protection design side of things and a little bit of case studies of actual things that we do as cathodic protection engineers, designing systems, looking at corrosion and failures and what we can do using cathodic protection to stop the corrosion or at least control it. So, yes, let's see what I got here. So this is my outline for today. After the first few slides that have pictures, the rest of them don't have pictures. So hopefully you can sort of not get too bored. If you do, I'll throw something at you. It won't be candy because I didn't bring any candy today. But I'm sure we'll find something to throw at you. Because this is for you, not for me. So I'm going to talk just basically corrosion as it applies to cathodic protection and how we design cathodic protection systems. Then we're going to talk about galvanic corrosion. I have one case study of a radio communication tower that fell over. And I was pulled out to that site to investigate why it fell over. Spoiler alert, there was no cathodic protection. Okay. Then I'll go through what it takes to design a galvanic cathodic protection system, which can also be referred to as a sacrificial system. It's where we're taking one metal to sacrificially corrode it to protect another. That's galvanic. Then I'm also going to talk about impressed current system design. It's very similar to galvanic design. Impressed current just has an external power source that we're utilizing. So I'm not going to go too much into detail because they're similar. I'm just going to talk about the differences when we're designing an impressed current system. Then I have a couple slides on AC interference and how to spot it, and also how to spot DC interference as well. And then just briefly at the end, I have a couple slides on tank bottom CP systems and how we design those. So again, this is for you. If you have a question, just stop me. And if it's going over your head, that's my intention, because I'm trying to sound like an expert just so that you can get something from it. But if it is going over your head, just stop me. I can walk you through sort of the details that are involved in these cathodic protection systems. All right, so corrosion. Everyone knows what corrosion is, how it occurs, and why it occurs. As it pertains to cathodic protection, we're putting energy into an ore to create a metal that we then fabricate into a usable item. Tanks, pipes, structures, equipment, they all have mass amounts of energy put into them, depending on the metal and what we're using them for, to elevate them to an unnatural state. And cathodic protection is trying to keep it at that unnatural energy state. Corrosion is giving off the energy diagram, cathodic protection takes metal, specifically steel, that is in the corrosion portion of the pore bay diagram and adds electrochemical energy to it. And on the y-axis, you can see it going more electronegative. So we would cathodically protect something and go from the red star into the green star. Okay? Is it advancing online?
It's good.
Okay. So this is important. We're doing two things when we cathodically protect a metal. Number one, we're putting electronegative energy into it. So on this y-axis, it's going down from the corrosion area into the immunity area, which is immune from corrosion. The second thing is we're increasing the pH. We're becoming more alkaline. We're going right on the x-axis from a more neutral pH to an alkaline pH. So that's why you see the green star over here, which is still in the immunity section of the pore bay diagram. So that's what we're doing with cathodic protection. No questions?
So how do you change the pH?
I'll get to that in 2 slides.
Okay.
Yeah.
That was my question.
That's your question? Okay, so the pH is only changing on the surface of the metal. Okay? So if you have a pipe or a structure that's buried in soil, the pH of the whole soil environment is not changing. It's only changing due to the chemical reactions that are occurring on the metal surface. So if you were to test the electrolyte, the soil or the water that's in direct contact with the metal surface, that pH is going to be higher. And that's due to the chemical reaction, which I'll show you in 2 slides. Okay, these are all the factors that affect corrosion. And when you're a cathodic protection engineer and you're looking at designing a system, you need to factor in all of these different elements that are surrounding whatever the structure is that you're intending to protect. Okay? So if there is a galvanic issue with different metals touching each other, that's what you're trying to combat. Okay? If there's a temperature in the environment that is increasing your corrosion, your cathodic protection system has to combat that. If the temperature is lower or the soil resistivity is higher, okay, the environment isn't as corrosive naturally, so your cathodic protection system doesn't have to overcome as much. How much oxygen is in that environment is a big one, because oxygen, of course, is a depolarizing agent. It increases the corrosion rate. So these are things that affect the corrosion rate, and when we're designing a cathodic protection system, we have to take each of them into account so that we can eliminate them or at least control them. So that's why I have this slide up there. And then, of course, the pH of the environment is super important, because as we'll get to on the next slide to answer the 2 questions, okay, cathodic protection is really a phenomenon of pH. We are chemically altering the environment in direct contact with the surface of the metal that is corroding or wants to corrode to protect it from corroding. It's that direct contact environment of the soil, the water, the atmosphere, whatever it is that's causing the corrosion. So that's what we're trying to combat with cathodic protection. And that occurs in these reactions. So we talk about anodic and cathodic. Anodic is where the corrosion is occurring, and you can see in the chemical reaction, why is the pH so low?
Because of the H plus. Yeah.
That's correct.
Proton.
Okay, so you can see when you have corrosion, it's very acidic because of the chemical reaction that's creating the hydrogen ion. Okay, that low pH, that acidic environment in direct contact with the metal is indicative of the corrosion. On the cathodic site, and remember, cathodic protection is the intended purpose of cathodic protection is to turn all of the surface area that is exposed, potentially corroding, to cathodic. And as we apply cathodic protection, these are the reactions that are taking place. So why does the pH go up?
OH minus.
Answer that one.
Because we have OH minus hydroxide.
Right. That's right. So as part of the cathodic chemical reaction on the surface in the environment that is corrosive, we are creating hydroxyl ions. Okay. We are altering the pH in direct contact with the metal. And that is what is protecting the steel. Okay. Which metals are amphoteric? Does anyone know what amphoteric means?
Yeah, it's an after base. Aluminum.
Yep.
Yeah, so aluminum, we actually, when we protect aluminum, we want to actually minimize this reaction. Okay? We can't let the potential of the aluminum get too electronegative because the pH actually goes into the amphoteric range where it corrodes at a high pH. So that you also have to combat with cathodic protection. So if you were to protect aluminum, you're not going to do it with an impressed current system, which I'll talk about. You're going to do it with a galvanic system, and you're going to use
Something more negative than aluminum.
something more electronegative than
magnesium?
aluminum, but not too electronegative. Does anyone know what metal that is?
Isn't magnesium?
On the galvanic series.
Depends on the environment, isn't it?
So here's aluminum.
Zinc. Yes.
We have to go more electronegative, but not too electronegative. We only have two choices, really. Zinc and magnesium. Magnesium sits at about negative 1.75. The copper sulfate, which would push the pH too high and cause corrosion to the aluminum, which is amphoteric. So you actually use zinc to protect aluminum.
But it depends on the environment, right? Because in some environments it would be the other way around.
Depending on the pH
Yes,
of the
yeah.
environment.
But this is like a neutral salt. Yeah.
In neutral. But yes, that's correct. Because anytime we talk about corrosion, that's a good point. Because anytime we talk about corrosion, corrosion is defined as the degradation of a material in its environment. So if the environment, which is the electrolyte, has a different pH, that's going to determine the corrosion rate of the metal. So you're correct. So I'm just talking in a neutral environment. All right. 4 elements in a corrosion cell are
On the screen.
terrible. No, terrible. Okay, we talked about anodic and cathodic sites. That's on the metal itself. The electrolyte I'm talking a lot about because that's really the only thing that we can alter. The metallic path is the connection between the ionic site and the cathodic site, which is the structure itself, which is the metal. Unless we're talking about galvanic, where we have 2 different metals touching, then the metallic path is the contact between the 2 metals. Okay?
Which could be isolated, right? So or insulated.
Yes. So to combat corrosion, we have to remove one of these 4.
Yeah.
Okay. If we're talking about one pipeline or one structure that has anodic and cathodic sites, you're always going to have the metallic path. If we're talking about zinc and aluminum, the metallic path between those 2 is the contact. So if we can dielectrically isolate those 2, so there is no transfer between them, that's how we would eliminate the cathode and the anode.
But
in a
you can
galvanic.
only do that in an environment that it has no flow, because when you have flow, one of them could deposit on the other. So that happens in water pipelines or in the mouth. So, for example, amalgam and gold, if they are far away, the gold can deposit on the amalgam and then still cause galvanic corrosion.
Due to the conductive nature of the fluid.
Exactly, because of some solubilized and then redeposit.
That's a good point, because if we're strictly talking galvanic, the metallic path is when they're touching because they're conductive. But if they're close and we have a conductive medium like water or salt water that's highly conductive and they're close enough, the connection goes through that conductive medium. Yeah. But the way to combat that is to coat, to put some other dielectric barrier between the two. Is how we do that. Okay. I'm done, Ed. Or maybe one more slide, and then we'll get into some more detailed stuff here. So talking about galvanic corrosion, again, it's that coupling of the two. So you'll see this a lot with rivets, bolts, different metals that are touching. And you want to actually isolate in between the two to eliminate that. When we're talking about galvanic corrosion and designing cathodic protection systems that are galvanic systems, we're limited on the galvanic series by the voltage, which is the energy potential difference between two different metals. Okay. Magnesium we use a lot as a galvanic anode in a CP system to protect steel. Why? Because when you subtract magnesium, which sits at about negative 1.75 to copper sulfate, from a steel that you're trying to protect to the CP criterion of negative 850, you get about 0.9 volts. Okay? So that's a rather large driving voltage. That's why magnesium is used in soil. We talked already about using zinc for aluminum because aluminum is amphoteric, but that driving voltage is very small. We're only talking 1 or 200 millivolts there. The example which I'm going to show next in my first case study is copper versus steel. So remember this here. If you were to touch copper to steel, steel is right here, and copper is down here. So they are relatively close together. The difference is about 0.3 volts or 300 millivolts, which is not a lot of driving voltage. So the corrosion between those two galvanically coupled metals is going to be slow. However, if you leave it over time, it will eventually fail. It has enough corrosion there. All right. This is my first example and the best one because it has pictures. So I was called out almost, well, probably maybe 12 years ago now to a radio communication tower. So you'll see on the top of the hills as you're driving a lot of radio towers, communication towers. And typically the smaller ones will have 3 guy wires that support it from falling over. Okay? Larger ones have still groups of 3, but they have more. This one had 3 guy wires. It'd probably be about 250, 300 feet tall radio tower. You can imagine how tall it was. I got to site and it had fallen over. It was in pieces, and I was looking around, and I'm like, okay, well, before I even got there, I'm like, okay, well, I knew why it fell over. Okay, who can tell me why it fell over? That's 3 guy wires that were attached with these. This was the support. They're backwards C channels put together. They went into a concrete block to weigh it down and keep it in the ground. So why did it fall over? Pretty obvious. One of the corrosion. Okay. Where did it corrode? It actually corroded. The failure point was actually further down, right where it went into the concrete. Okay, that's where it corroded. That's where it was probably about a meter and a half deep at that point. Okay, so there's not very much of this human soil, but you can see clearly, you know, above ground it wasn't corroding. It's galvanized steel C-channel, wasn't corroding above ground. I want to say it was in the 10 to 15-year-old tower. Okay, galvanized rod, C-channel, and it failed down here by the concrete. Only corroded in the soil. Okay, so that's why it corroded. There was no cathodic protection. But so then I got looking around, and I'm like, well, it's galvanized. Why was galvanized steel corroding?
Because it has no electrolyte. In atmospheric conditions, galvanized steel does not help because there is no electrolyte. So because theoretically, if everything would be immersed, the zinc would be consumed completely before something else happens. But here it doesn't, because you get the corrosion on one side, but the galvanized steel or the zinc on the other side doesn't care because it doesn't see if there is too little electrolyte flow. So that's the problem with using galvanized in atmospheric conditions, because it's like there is no. If it would be immersed, it would work.
Okay. Well, that's what you would think. Okay. So you can see that. So this portion of it was above ground.
Yeah.
So the galvanized stuff that was in the atmosphere wasn't corroding.
Yeah.
What was buried in the soil was corroding.
But the galvanized steel above soil did also not protect the other steel inside the soil.
Oh, I see.
Because it was not immersed. If it would have been immersed, it would have been visible and it would have been protective.
Okay, valid point. Because there's no connection. But this was zinc too. This was all galvanized.
Yeah. But this was completely consuming the zinc because it was in the soil where there is moisture.
I would say, without what was going on, which I'm going to talk about, if that wasn't happening, this wouldn't have corroded. The galvanic in the soil
Would still
should
be
have been
intact.
fine. It was only 10 to 15 years old. It's in the soil, it's galvanized. It should have been fine. Okay, so there's something else going on here. Last slide, I told you to remember something.
Steel.
No.
Copper.
Copper. Copper. I think I must did I write it on there? Is it written on there?
It's written on there.
Oh, you guys.
Yeah, you read actually the slides.
Yes, so what's taking place here is that there was a copper grounding rod. And you can't really see it, but it's in that yellow sheathing. There's a copper grounding rod. It's all radio communications towers, power lines. Large structures have antennas on top of their building. Why? Because they're going to get struck by lightning. Okay? They're metallic, all they're going to get struck by lightning. So all structures like this have to be grounded so that when it does get struck with electricity, it goes to ground. And the best metal to use for grounding is copper. You use like a 2-aught, very thick copper cable to ground most things, right? This structure had a copper cable. I think it was like 2-aught, so about half an inch thick, or 3/4 of an inch thick copper cable that went. It was connected to the structure. So again, that's the galvanic couple between copper and galvanized steel. And the copper went to ground. It was wrapped around the concrete block that the support went into. Okay? did it corrode?
There was connection.
Galvanic corrosion due to the couple of the copper, which was connected to the galvanized structure, steel. And going back to the two previous slides ago, I told you to remember that driving voltage number of what?
0.3.
0.3 volts. So that's copper to galvanized steel. Which one, steel or copper, which one is anodic?
Still.
Steel. Okay. Steel is anodic to copper. So when I first got to this side, I was like, well, obviously it's corrosion. Obviously a guy wire broke because of the corrosion. Why did it break? I got to it, I'm like, well, it's galvanized, it shouldn't be corroding. There's something else going on here. I'm looking in the hole, and what do I see? Copper. What color do you think the copper was in?
It was red.
It was beautifully red.
It was so
Wow.
pristine. And I looked at the copper and I thought, so I asked the guy on site, I was like, well, where did this copper come from? Why did someone, because I thought, I was like, oh, someone just threw some copper cable in the hole. Because it looked brand new,
So,
right?
yeah.
So he's like, well, no, that was the ground cable wrapped around the concrete. I'm like, how long has it been there? Well, designed with the power. I'm like, okay. You know what the issue is? Galvanic corrosion. The copper is the cathode. The steel is actually the anode. Okay, so the copper is being protected
Like a
cathodically and galvanically from the steel. So the steel is corroded to protect the copper. But in doing so, the support went away. Some interesting numbers from this site. When you take a potential of steel, it's sitting at negative 650. So that's below cathodic protection level. That's telling me that it's not cathodically protected. It's actually very anodic. The pH, so wrote down native and base, but base would be like just around in that area was 4.5, but it was 2.75. The best I could get a sample right next to the steel, very acidic, because it was corroding, obviously. And then soil resistivities would tell us how corrosive the soil environment is. And then it was obviously pitting, it was corroding, it general corrosion, it necked off right close to the concrete wall. Any questions?
Was there some crevice as well between the concrete and the steel, and that was why it fell off there?
No, there was like an inch or two sticking out of the concrete, so it happened very close to the concrete.
Because that was the closest spot to the copper that was already immersed in soil?
No, it didn't. It didn't have to do with the proximity to the copper. The copper, in a cathodic protection design, like if I was trying to protect copper, this would be a perfect way to do it because there was a separation distance from the copper.
Yeah.
They weren't close. I mean, relatively they were because they were in the same concrete block. But the metal and steel went into the top of the concrete. The copper came around and then back up. So the whole length of the copper was red. Like it looked just great. So there wasn't a spot where the copper wasn't being protected cathodically due to the proximity of the two metals.
So the connection between the copper and the steel, was that something accidental or?
So you do that on purpose. So the copper, which is intended to ground the structure, has to be connected to the structure.
I thought they connected to the top of the, for example, the
It
top.
doesn't matter where that connection is.
But it has to be electrically connected,
Connected
right?
to this.
Yeah, it could be at the very top, middle. It could be right there in the hole. Yeah, it could be totally.
So the error was that if you do have grounding wire, you have to think about cathodic protection.
Correct. So a lot of designs that we're running into right now, we're dealing with what we call AC mitigation systems. So for this, where we have pipelines that share the same right-of-way with overhead power lines, you're inducing an AC voltage onto the pipeline. And so we intentionally ground our pipeline using copper. So either a copper cable in the ditch or a copper rod to ground the pipeline. So that's intended now. But as we install these systems, we have to think about now protecting both the pipeline and the copper grounding using cathodic protection. So that is, we do have to take that into.
Spencer, what would you do in this case if you were not, because you've got to ground it. The grounding, it has to be copper. The grounding has to be attached to the thing.
Yep.
You're going to use, galvanized steel is used in all these applications
Yep.
still today and will continue to be. So what's the solution?
It's the easiest solution in the book. So you fix this using a galvanic cathodic protection.
So you attach some zinc to the galvanized steel? Or?
So we have steel, we have copper. We just choose a metal that's more electronegative. So in this case, I did designs for magnesium anodes to protect both the copper and the steel.
And is that done in practice now?
Yes. Yeah. So this one was eye-opening because I'm like, obviously this is the problem. Simple design, just put one magnesium anode in the hole, protect it, it'll protect both the copper and the steel. Okay? Very cheap, inexpensive, simple solution. And this company went and put it in at all their sites. Yep. Very simple solution.
So how do you have like alarm system when the magnesium anode is consumed?
You check it periodically. You check it every year. You take a potential on it. The potential, again, a magnesium anode sits at negative 1.7 or 1.75 volts for copper sulfate. So every year you're going to go out there and you check the potential of the anode. When it starts dropping, so like 1.4, 1.2, now you know it's being consumed, so you have to replace it.
So I thought we designed for like 20 or 30 years, but do we still need to do that, the inspection every year? Or for example, for the after installation, you need to just check after 5 or 10 years?
So if it's a regulated pipeline, you are mandated to check it every year. If it's not, if it's a water pipe or if it's a communications tower, you're not mandated to check it. But you should, obviously. Magnesium anodes, so the design life for a magnesium anode for something like this is going to be like 15 to 20 years. Okay? Magnesium anodes don't last longer than 20 years. When you design this system, you would say, hey, I need to get at least 15 years out of this. So you could leave it for 5 years and then check it at 10 years if it's not regulated. But you run the risk of it failing prematurely if you don't know about it. Yeah. Okay. This is a calculation that I just did really quickly on that previous example to see how much steel metal was lost. Okay? You can do your simple weight calculation based on steel. So steel is going to be consumed at 9.13. That's the theoretical consumption rate of steel per amp year. So every year, if there is 1 amp of current flowing off of the steel, in that case to the copper, you would see 9.13 kilograms of steel corrosion. Okay. Again, copper minus steel is 0.3 volts. So when we put that 0.3 volts, which is very low, into Ohm's law, we can figure out how much mass is lost on the steel. To do that, we have to say, okay, how much steel do we have? And the steel that we have that's the anode is only what's buried. Then we have the copper that's in the ground, and we calculate the resistances of that circuit and plug the resistance in. We have a surface area, we have a resistance per surface area, calculate that out to figure out how much current there is in the system. Then we use that current in our weight formula and our theoretical consumption rate of steel to calculate how much metal is actually corroded. For this one, I used 15 years. I believe that's how old that tower was. And you would get about half a kilogram or a pound of steel that had corroded over 15 years. And it gets to the point where all that metal loss from the steel was enough for a re-break. All right. Does everyone know the difference between a galvanic system and a press current system? Yes? No? Maybe? No? Sort of. I talked a lot about galvanic systems already, so essentially you have two metals. You don't have external power, you're just using that voltage. Okay, the 0.3 volts copper to steel, the 0.9 volt magnesium to steel. That's a fixed driving voltage. In press current system, we use an external power source, so now we can alter how much voltage we're using or how much we need. Okay, that's the main difference between the two. And in press current systems can obviously protect much further away, bigger systems. But you also have interference effects when you're talking about in press current. So let's get back to the galvanic systems, and I'm going to do design here. I wish I had a picture or I could draw something, but so here's a case study where we're asked as a cathodic protection engineer to design a system that's going to protect 3 storage tanks. Think about a gas station. When you go to a gas station, you can get regular fuel. What else can you get, Ed?
94.
Yeah, you can get different grades of fuel. Okay. Well, guess what? Each grade of fuel and diesel, they're all going to have their own storage tank because you're not mixing them. Okay. What Ed wants is 94. He doesn't want 94 mixed with 91. You know, 94, that's like a high-performance sports vehicle. Anyways, each one is going to have a storage tank, okay, a small storage tank. In this case, we have 3 storage tanks. They're 12 meters long, 3.6 meter diameter. They're buried in the soil. They're sitting, the 3 of them are sitting beside each other. They're steel tanks. What's going to happen? Corrosion. Corrosion's going to happen. Okay, I think this case, the steels were actually coated. I think I have 0.9.
Yeah, 10% bare.
Yeah, 10% bare. So that essentially is telling me that is coated. You don't have the entire surface area exposed to the electrolyte. You only have 10%.
Can I ask you a question about this? Because this came up when I was teaching last term. So let's say I buy a pristine piece of pipe, like kind of I put it in the ground. What do I assume is the percent bare?
Yeah, and I didn't put a picture of the table. There's a table.
Okay.
You can theoretically assume a value, or you can actually go test.
So in your experience, what is the 1%?
So brand new Trans Mountain pipeline with fusion bonded epoxy coating,
Yeah.
which is excellent. We essentially go bare, poor, fair, good, excellent. There's a table with windows and an excellent FE coating on Trans Mountain is essentially 0.00 After 20 years, it's about 2 to 10 times worse.
So it's still less than 1%.
Yeah. Yeah. So this is like 10%, which is very poor. Maybe someone just put some, I think it was coal tar, they just slapped some goo on it. It's old, it's sitting in the ground, and it helps us to design a system better than 0.0001% there. But that's the fusion bonded epoxies of right now. That's how good they are. Something like, I'm going to say like 2005 maybe, like anything prior to 2005, it's like 5 times worse than that. And then the 1990s, we're talking like 20 times worse than that. So when you get back into like our original Trans Mountain line, so we had this fusion bonded 0.0001% bare, right next to our old 1950s vintage coal tar enamel coating, which is more like this. It's actually only about 1%. It's 1%. Is what our old coal tar is, not 10%, but 1. But that's the difference. All right, so we're designing a system. The coating is about 10% bare, exposed metal. So the first thing we do is we calculate the exposed surface area of the metal. Okay? The stuff that's coated and protected, it's not going to be corroded. Only the exposed stuff where the coating is not doing its job. In this case, it's 10%. We do a surface area calculation, multiply that by 0.1, which is 10%, multiply by 3, because we've got 3 tanks to protect, and we get a surface area of 489 meters squared. Okay. Then, what I was just talking about with Ed, in this case, we're going to assume, based on the percent bare, how much current the cathodic protection system needs to provide per surface area, right? So in this case, we're going to use 2.15 microamps per centimeter squared. Okay. Next, we're doing a galvanic system. We're going to use a magnesium anode. Magnesium anode, in this case, well, this is a theoretical consumption rate of a magnesium anode, 0.125 amperes per kilogram. So if you invert that, you get kilograms of consumption per ampere. Okay. Magnesium anodes, I already mentioned, you're not going to get more than 20 years out of them. That's because magnesium especially, but all metals will self-consume. Okay? It has anodic sites and cathodic sites on the metal itself. It's going to self-consume. When you go to the store, who's the last person in here to buy a AA battery? Anyone? Anyone?
AAA battery?
You guys need to have some kids so you can put some batteries in your toy. What did you buy?
A AAA?
A AAA? Yeah, AAA. What's the voltage?
I just steal them from work. Why do you buy them?
No, I
Okay,
didn't buy
okay.
them. I got them from a store.
Yeah,
Fair enough, but he used one.
Yeah, I use them.
Okay. What was the driving voltage on that battery?
For the torque wrench that I got. So
Who knows that answer? What's the driving voltage?
1.5?
1.5 volts. Okay, it says it right on the battery. That's the driving voltage between the positive metal and the negative metal. 1.5 volts is more than what we're doing with galvanic. Okay, those are nice, good metals. 1.5 volts is written on the battery. What is written right next to it?
Oh, it gives you an average, doesn't it?
No.
No?
No, the rechargeable ones do. I'll give you a hint when you buy a jug of milk.
Oh, there's an
Expiration date.
Yeah.
There's
It's
an
self-discharge.
expiration date on the battery. And you'll think, well, it's just a battery, I'll just use it. No, because it self-consumes over time. That's why a battery has an expiration date. In this case, we're using 50% efficiency, because even if we're not driving the magnesium hard enough to really protect the system, what we're trying to protect, it's going to be self-consuming. So it's not going to last, even if we're not using it. Okay? So we got 50% efficiency. Plug that in to figure out, based on our current required of 1.06 amps, and our life, we're trying to get 20 years out of this magnesium anode, and putting out 1.06 amps, how much weight of magnesium do we require to design this system? And we get 170 kilograms of magnesium. Okay. We also have a safety factor on magnesium of 85% utilization. Utilization implies that over time, as you're consuming this magnesium anode and get smaller and smaller, you get to the point where it either necks off or it breaks when it gets really small, and you're not going to utilize 100% of the weight. Okay? You're going to be left with this little stub of anode, and it's not going to work anymore. But you're still left with some mass there. We have to factor that mass into our calculation. So we use 85% utilization factor. We're going to multiply that by our 170 kilograms inversely to get 200 kilograms. So really, we need 200 kilograms of magnesium anode. When you go to get magnesium anodes, there's a table, and they're all different sizes. You can get 3 pounds, 5, 7, 9, 11, 14, 32. You can get a huge magnesium anode that comes on a crate or a truck, all different sizes and weights. So as a cathodic protection engineer, we now have to pick one. I got a bunch of these. Let's try using those. So first, we're going to pick 14.5 kilogram anode. How many do we need? Simple calculation: 200 kilograms divided by our 14.5, and we're like, oh, we need 14 of these 14.5 kilogram anodes. Okay, let's see if that's going to work. It's an iterative process. So now we use Dwight's equation to figure out the resistance of one anode in the soil environment. So we have the soil resistivity, which is the resistance inverse of conductivity of the soil that the anode is placed in. In this case, we're using 4,000 ohm centimeter. We have the length of the anode, the diameter of the anode, soil environment, and what else do we need? That's
Resistivity?
it. The resistivity. That's what we need to figure out. What is the resistance in the galvanic series circuit of that anode? Okay, and we get 30.9 ohms. Perfect. No questions?
I have a question.
Yeah, you do.
So the 4,000, you would measure that, right? Because, I mean, there's a wide variety of...
Yeah, if you want to be lazy and you don't want to leave your office,
Yeah.
you can assume, you can look at a record for the area, but 9 times out of 10, you're going to absolutely go to site, stick 4 pins. I don't know if I have a slide on that. I was going to, but I didn't put it in. You're going to do a soil resistivity test, which involves 4 pins. You inject a current into the soil through this outer pin. It goes through the soil to the other outer pin. That's a current. The 2 inner pins measure the voltage that's created in the soil from the test current. The 4 pins are spaced equidistant apart. If were to space them, let's do 2 meters, 2 meters apart, 2 meters, 2 meters, 2 meters, we can now calculate the soil resistivity at a depth of 2 meters. So yes, you would test the soil to get a resistivity value. Otherwise, you're assuming and you're just throwing a number in the equation, and you're not going to get an accurate result. So at all costs, if possible, go collect the soil resistivity reading.
If the soil has a bigger resistivity, you would need more anode material?
Less.
Correct. Yes. So galvanic systems, typically like 4,000, 5,000, that's like your max. Okay. Typically a galvanic system you want to be using in like the lowest resistivity you can. Okay. So if you're in Alberta and it's a nice juicy soil in a farmer's field, you could get 1,500, 2,000, 2,500 ohms centimeters, which is perfect for galvanic.
But it depends on the moisture, right?
Correct.
So if you have years of drought,
then your galvanic system is not going to work very well.
yeah.
Right? The more aerated the soil is, the type of grains that are in the soil, the moisture context of the soil, it all influences your soil resistivity. And the higher that gets, you can't use galvanic.
So if the soil resistance is higher, do we need more anode or less? Because it also affects the corrosivity of the...
Correct. So the environment is more corrosive, so you need more cathodic protection current. To get more current, as per Ohm's law, you either need a higher driving voltage, which means you're now going from galvanic to impress to get more voltage, or you need a lower resistivity of the soil, or resistance in the circuit, which comes directly from the resistivity of the soil. Because in this calculation of the resistance of the anode, you can see the resistivity is right here. So it's linearly proportionate. Okay. So if this resistivity goes from 1,000 to 10,000, the resistance is 10 times as much, which means you're going to get a tenth of the current using Ohm's law out of the anode. But in a, you know what I mean? Yes. Clear? Thumbs up, down.
Great stuff.
Yes, it is great stuff.
But
I feel
super
like I could get a
difficult
job
because
as
it's
a
fluctuating,
teacher.
right?
So seasonal effects are
Yeah.
real. Okay, so depending on the soil environment and how much the resistivity changes, you have to design your CP system accordingly. So a galvanic anode, you can't do much with it because you can't alter the voltage. The driving voltage is fixed. And the resistance of the anode is going to go up when it's dry. But as it goes up when it's dry, the dry environment itself is less close. So it's not as seasonally affected as you would think. If it is highly seasonally affected, like the spring is super wet versus the winter. Okay. The advantage to using a compressed current system, you can alter the driving voltage. Okay. So you have I'm going to answer this just because I want to talk about it, even though it's off topic, and we'll get to compressed current systems. But the rectifier, you can adjust the voltage, right? So you can go and be like, hey, it's dry right now. We got to crank up the voltage. Okay? You can actually get rectifiers that are constant current. So the voltage automatically adjusts for seasonal effects. Good? Okay. How are we doing for time, Ed?
What time? I don't know. What time is it?
Quarter after 4. questions are better than just me talking. All right, moving on with the galvanic CP system design. So now we have our resistance of our anode. We know what the driving voltage is, 0.9 volts between magnesium and steel. That's the polarized steel potential. Okay. The previous case study with the galvanized steel that was corroding, it was at 0.65. For this calculation, we're basing it on the cathodic protection criterion of -850. So that's where we go, because that's where we want to get it to and keep it at. So we take 850 magnesium and get 0.9 volts. We have our resistance of the anode. Now we do our Ohm's law calculation to find out that we get 30 milliamps per anode. Okay. We chose 14.5 kilogram anodes in this example. And each anode is only putting out, based on the solar resistivity in the environment, 30 milliamps. 14 times 30 milliamps gets us 0.42 amps. Our intended design current was, does anybody remember, it was a long time ago?
1.06.
1.06. We're trying, it's on there. I thought you were paying attention and then you're just reading the rest of the line down.
Well, they're related.
Yeah. Yeah, so we're trying to get 1.06 amps, and we're only getting 0.42. So now what do? We say, okay, I don't want to use these because essentially I would need like 2.5 times as many of these 14 kilogram anodes to get my intended current. Let's try using a smaller anode. So now we're going to go down to a 9 kilogram anode and see how many of those we need. And when we run the calculations, the resistance is different for a 9 kilogram anode because it's skinnier and longer than the 14.5. So when you do the resistance calculation, it actually comes out to be a lower resistance anode of 19 ohms. And when you plug that in, you can actually get more current out of the smaller anode, weight-wise, based on the configuration of it being longer. Okay? So you would use, there are different applications for different anode sizes and weights. Okay? The 14.4 is a more bulkier anode. It has its application where it's going to work here. It doesn't work in this example because we would need so many of them, and we're going to have so much mass there, we're not going to use it all. This example, we go down to a 9 kilogram, which is longer and skinnier. And get a better, lower resistance, more current. We're getting 47 milliamps per anode when we calculate it. And we find out that we only need 22, we're going to call it 24 of these anodes. If you have never seen an anode package before, this silver portion is the magnesium. It has a cable coming out of it. In here is a backfill. Typically like a Bentonite type backfill, just to lower that resistance to the soil. So we've got 24 anodes. Yeah.
So I remember in sometime when you want to initially polarize your structure, you need to apply a little bit more current or voltage compared to the rest of the time. You know.
Correct.
So does that work here in galvanic CP as well? Because that's I think for impressed current.
Either or.
Okay. So
depending on the soil environment. Seawater, so the more conductive the environment is, what you're talking about is what we call activation polarization. Activation polarization is dependent on the soil environment. So in seawater, what they actually do is they put anodes in place to get that activation polarization taken care of. And then after that, they don't need as many anodes. So the current that's required to activate the polarization in seawater is very high. But once it's polarized to a cathodically protected level, it doesn't need that much current anymore. It was the activation, polarization current that was required. Now it doesn't need it. In soil, we don't see that, really. It does exist, but it's not as sufficient enough for us to design around it most times in soil. Seawater for sure.
Thanks.
So for the back, was there a question?
Nope.
No,
Go ahead.
for the backfill, you mentioned bentonite.
Yep.
I know they use bentonite to like make things dry, not low resistance. So is it some kind of special mixture that is like wet or
So bentonite absorbs
water? Yeah.
and because it absorbs water and it's in direct contact around the magnesium, it lowers the resistance of the anode to the soil environment, makes it more conductive to it because bentonite retains the moisture, assuming that the native soil around it is going to still absorb moisture from rain and whatnot.
That's interesting because in the nuclear waste field, they
Yeah.
use bentonite to basically
To
isolate,
right.
remove water, but
Yes.
here, yeah.
Yeah.
Oh,
So it's a
interesting.
mixture of, I want to say 50% bentonite, 40% gypsum,
Ah.
and 10% something else. So it's not all bentonite.
Yeah.
Isn't there something conductive like coal or carbon?
That's in
yeah.
impressed current systems. Impressed current systems use petroleum coke-freeze or calcined coke, which is carbon powder. Yeah, for that backfill. Because there you want the carbon actually consumes before the anode. So you extend the life of the anode. That's why you use a conductive carbon backfill in impressed current systems. In galvanic, you want to lower that resistance of the metal to the soil. And to do that, we use this gypsum bentonite mixture to absorb moisture and make it conductive to the soil around it. To answer that question, a lot of time, well, you're supposed to actually, when you put these in, you're supposed to water them, right? So because the bentonite is designed to have that moisture. But you only need to water them when you install them.
Yeah.
After that,
It holds it, right?
it holds it, and the soil environment itself gets replenished with rain and everything. Yeah. Good. Okay, I think we're done with galvanic. So just to finish this one, 24 anodes, 3 tanks. You would literally just space them out so that they can be all around the structure and protect every little. Because a lot of times the tanks will be close together, where you're going to want to have the anodes in between them and protect the whole structure. All right. Impressed current systems. I'm not going to go in depth as much because it's the same principle. Okay, we're going to be collecting a resistance of our anodes. But also, what we have in an impressed current system that we don't have in galvanic systems, we have a lot of cable. The cable adds resistance. Okay. The structure itself has its own linear resistance. We have to add up, and in this case, those are the 3 big ones. Okay, but there's other portions of the circuit that have resistance to them as well. Cables, you can look them up based on the size of the cable. They have a linear resistance per length. In impressed current systems, sometimes we're talking like hundreds of meters of cable. And you'll think, oh, that cable is not a big deal. If they have more cable, it's not going to affect my cathodic protection system. Well, it does because it adds resistance to the circuit. Okay? The more cable you have, I'll put my ground bed a kilometer away. Well, now I got to run a kilometer of cable. And that kilometer of cable has a linear resistance per meter. And I add that up, okay, and I get a resistance. So now I have to take the resistance of my ground bed, my anode, which I did in the galvanic system. The only difference is how you configure your ground bed. There's different formulas. So if you have a linear ground bed, that's one formula. If you have a vertical one, that's another. And okay, the difference is, I go back to Dwight's formula. This is Dwight's formula for a single anode. So it has a length, a diameter, length, resistivity. The length and the diameter are what influence the resistance of the anode. In an impressed current system, you have multiple anodes to produce your current. Well, the Dwight's formula has another portion in here when you start introducing multiple anodes to calculate an overall ground bed resistance. So you have what's called a spacing factor. And that's if I put one vertical here and I put another anode here, 1 meter apart, the spacing is 1 meter. So that gets put into the formula. The further away I get with them, there's no what's called mutual interference between the two anodes, which diminishes the effect of having multiple anodes. Okay? So if I space them too close together, they start interacting with each other and they don't put out as much current. What's interesting with an impressed current system using multiple anodes, if you do space them close together, the ones on the perimeter are going to put out more current. If they put out more current, they're going to consume faster, right? And then you get to the middle anodes. So an impressed current anode resistance uses a different formula based on the spacing between the anodes. This is what an impressed current anode looks like. Just typically cast iron, you can use mixed metal oxide, you can use graphite, you can use scrap metal, you can use pipe, you can use copper, you can use any metal because you're forcing a voltage on. Typically, cast iron is a good one. Have a cable coming off. So we're going to calculate the resistance of the cable using the linear resistance and how much cable we have. We also calculate the pipe resistance. So the pipe can add resistance to our circuit based on its own geometry. So you take the inner diameter, the outer diameter, the resistivity of the steel, and how much you have, and you calculate your pipe resistance. So we have our ground bed resistance of the anode, cable resistances, and the pipe or the structure resistance. We add them all up to get our resistance, same as galvanic. Now we have a resistance of our circuit using Ohm's law and the voltage output of our impressed current rectifier. We can get our intended current. So it's not really too different. This remote earth calculation is important. When you're installing an impressed current system, you can't put the anodes too close to your intended structure to protect. Okay? If it's too close, all of the current off of the ground bed is going to go right there. 60 degrees this way, 60 degrees this way. If I'm too close, this is my structure. I'm only going to protect that much. But as I get further away with my anode bed, it protects more and more and more. Not only that, the further away I get, I put into this calculation the current output that I'm putting out from the ground bed, how far away I am, the soil characteristics, and I get to what's called remote earth. Remote earth, you never get 100%. Typically a design, you're going to get about 95% is great. That just means that once I'm 10 meters away in this environment, I'm remote Earth, which means that ground bed is going to protect kilometers and kilometers away. Okay. Based on the soil, the output of the ground bed. If I have a ground bed that's producing more current, I have to get further away. That's why a lot of times, urban environments, we do what's called deep wells, where we drill down 2, 3, 4, 500 feet deep and put our anodes all the way at the bottom of the hole. Why? To create a separation distance to get to remote Earth, so that that ground bed can not only protect right here, but it can be projected along the pipeline. The issue with any impressed current system and trying to protect kilometers and kilometers of pipe is that you lose its strength, its signal strength, the further away you get. It's just like anything else. The further away I get along my intended structure, the less protection I'm going to get. It just diminishes. We call that attenuation, and there's a calculation for that. This is the simple, it looks simple, but it's actually not, because RS and RL, which is the long signal resistance, there's a separate formula to calculate it, and a separate formula to calculate the other resistance values plug into this. Okay, so that's based on the pipe characteristics, coating type, size of pipe, how far away. You can do this calculation at different lengths to see how far you're going to get. So let's say I want to protect this 10 kilometers away. You plug this into the two calculations based on your output, soil characteristics, the pipe characteristics, to figure out, okay, I have 1 volt of driving voltage right here. How much driving voltage do I have 10 kilometers away? Is that enough to protect 10 kilometers away, or do I need more output? So that's, as you get further and further away, you lose power. All right, any questions on press current systems?
The pipe resistance, would that also include the coating type? Yeah. And so it goes into the original one and in the attenuation, right?
Yeah, so depending on the type of steel, you have a value here. You have to look that up on the table based on the type of steel. OD minus ID is the thickness of the wall of the steel. Does that influence the longitudinal resistance of it?
But the condition of the coating would also matter, right?
Yes. You also have the external surface.
Yeah.
And then here you have the other factors of the soil, right? Which affect the resistance to the earth at certain distances. So those are all taken into account. Yeah. Questions about impressed current systems?
So will you talk about cathodic delamination as well?
I'm gonna plug my laptop in. What's that?
Cathodic delamination of coating?
That's a good subject. Yeah. So what you're referring to is the reaction on the surface of the steel. What are we creating?
We are, yeah, OH minus. But the question is about hydrogen, right? Yeah, hydrogen gas. So it depends on the pH. Oh yeah, here.
Yes, you create hydrogen.
Yeah.
And hydrogen atoms, when they link up, where they create
Yeah.
gas. And that then
Bubbles.
bubbles
Yeah.
and can affect your coating. But it's not the hydrogen, it's the hydroxide,
Ah.
right? Which increases the pH.
Yeah.
And sometimes the pH can affect the adhesion of the coating. Yeah. They were also concerned about hydrogen embrittlement caused by the hydrogen ions getting into the steel.
Is that an issue?
It's a theoretical issue.
Because we had this yesterday, we had ATCO talking about, yeah, if you just add up to 20% hydrogen in natural gas pipelines, it will not affect hydrogen embrittlement. And that sounds, for us that always think about like reactions and then hydrogen embrittlement, it sounds like wrong. But
Yes.
yeah, okay.
So theoretically, yes. There used to be, they were quite concerned about it, and they thought that excess cathodic protection was leading to possibly two things. One, blowing off the coating, which is true. We can create these reactions on the surface that will affect the adhesion of the coating, and the coating will fall. That's true. Okay. You can blister the coating. But inside that blister, where it's popped off from the adhesion being lost, you have a liquid. And the cathodic reaction, if you have cathodic protection in there that's doing that in the first place, the cathodic protection is creating hydroxyl ions. So the liquid that's in that blister has an alkaline pH. An alkaline pH, which I showed on the 4-wave diagram, puts the steel into immunity from corrosion.
But it might affect the adhesion of the coating more, right? Yeah.
Correct.
Yeah. Okay.
This is why I always say cathodic protection, coatings.
Yeah.
They work together, right? In the galvanic example, I said 10% bare.
Yeah.
What does that really mean? It means that corrosion is 90% stopped because I have 90% protection due to my coating. Great. Cathodic protection has to pick up the slack for the other 10%. Okay. So if you already have a structure that's protecting 10% and it's affecting the coating adhesion, making the coating work, yes, but it's very minimal. So you might go from 10% to 12%. But you have cathodic protection there working with the coating. So in my world, I always kind of laugh because I think, well, we're doing the same thing, we're working together here. Yes, I'm affecting you. CP is affecting the coating. Yes, it is. Depending on how well the coating is adhered, how well it was applied, what is the age of that coating, yes. I can have a greater effect with my cathodic protection, but I'm working together with you already.
Yeah.
So I kind of laughed at that one. So that's what's called coating disarming due to cathodic protection, which is real. It's minimal, and it's combated and mitigated with the same thing that created it.
Yeah.
That's one thing. Second thing is hydrogen embrittlement. They used to be worried about it from cathodic protection, not so anymore. There used to be an upper limit to our cathodic protection criterion of 1.2 volts to copper sulfate. It's not a criterion anymore because it's not proven to have detrimental effects linked to cathodic protection.
Yeah, you didn't see any like embrittlement cracking or something. Yeah. Okay.
Yeah. Okay.
Good.
All right, I think I have like 15 minutes. I'm not sure all asleep. Who needs some candy? I don't have any. There's snacks. You can just get up and have snacks if you're falling asleep. Okay, I got 15 minutes or 10 minutes, somewhere in there. I'm going to talk a little bit on an example case study of the interference. Okay. Ed's seen this slide before, but I'll go into a little bit more detail. This is some cathodic protection data. And we're trying to achieve cathodic protection criterion at this site. We're trying to get to our blue line, either at negative 850 to copper sulfate or 100 millivolts, the same straight across blue line. We measure the instant off polarized true potential of our pipe, which is our red line. And if we're above the blue, great, we're talking protected. We went out to this site and did a close interval survey, CIS survey, every few meters, collected data points. And we got to here, and our potentials started dropping below criterion. And we're like, what's going on? Well, you do some walking around and you find out why. Before I get to the why, let's go to this slide, which is now going to explain what's happening when we see different potentials, okay, when our potentials are changing. To measure our cathodic protection potential, we're trying to measure what's called a true instant off potential, polarized potential. That's what our criterion is based on. When our rectifier is on, we have an error in our measurement. The error is because I'm taking a reading on surface with my reference cell and my voltmeter on surface. And here's my pipeline that I'm trying to take a potential on. When the rectifier is on, there's current flowing through the soil to our pipe. And it's that current flowing through the soil that gets in between our measurement circuit. Okay? So we have to do what's called interrupt our rectifier to get rid of that error, which is the on potential and now the off polarized true potential. You can see the green line is our on. That's with our rectifier on. It has error in it. We interrupted it, we get to our red, which is our true polarized potential. Now, if we are in a good cathodically protected situation scenario, we have negative 850 off. Our on is more electronegative, negative 1000. That tells me that current is flowing through the soil in the direction of the pipe, according to this structure. Because, you see what I'm doing? I'm looking at this one. Negative 1000 on, rectifier on. The polarized potential is more electropositive, which tells me that the current is flowing in the direction of the pipe. It's going to the okay. If, for example, we have a reverse shift going on, where our on potential used to be up here, now it's here. 900 versus 950. That tells me what? When I'm measuring on versus off with my reference vector, there's something opposite going on in the soil. What's going on is that there's current, the net current in the soil is going away from my pipe. Okay? Not to get too technical, and I know I've lost some of you, but that doesn't matter. Because our off potential is still more electronegative than 850. So we're still achieving criterion. it just tells me that the error in the on measurement to the soil is telling me something different. It's telling me that there's more current flowing away from my pipe than is going to it. But there is sufficient current flowing through my pipe to get more electronegative than 850. We're at 950. So we're actually okay, and I'm not concerned. Now, if we have that same reverse shift scenario, negative 700 millivolts on, negative 800 millivolts off, more current is flowing away from my pipe than going to it. The difference is now I'm not meeting cathodic protection criterion. So that's what I would call current discharge from my pipe, and I have the threat of corrosion because I'm not adequately cathodically protecting the structure. A little difficult to understand, but anyone follow that? Anyone? Okay. Yeah. Now, even though I don't meet 850, I'm at 800. What can I do? Well, I can depolarize it to see if I get 100 millivolts to achieve my 100 millivolt criteria. And that's what we did in this example. We took a depolarized reading, which is the purple, and now we subtract the purple from the red, which is the off. Sorry, the blue here, the light blue, the aqua, is the depolarized reading. And I'm subtracting it from my off to get my purple to see if I'm more than the 100 millivolts. That being said, this example, I'll show you the picture. Why were we seeing the depression in our potentials? It's because we had interference from a foreign CP system that was affecting our readings. That's what was happening here. Any questions on that?
Was that one also a pipeline, or what was that one, the foreign one?
So the foreign one was protecting a water pipe that was crossing the highway. I think the rectifier was up near the top. The ground bed was there. It was protecting a foreign water pipe, a case crossing the highway.
But you do not always know this kind of sources, right?
You don't know.
Yeah.
So what's important to note here is we did our survey, we got our data, and we're looking at the data, and we're like, something's going on there. Well, then you go to site, you walk around, and you're like, oh, there's a ground bed right there, and it's not ours. It's affecting us in our readings, but it's foreign to us. Okay? So what can we do? We can bond to them. We're part of the same CP. We can, what we actually did is we put supplemental CP hotspot to increase our potentials at that site. There's a few options.
Did you also let them know that they could have also some interference from your system?
Yes, we did. We couldn't get a lot of information from them, and they hadn't even been out to, again, it was a water casing, so they weren't going out every year, and they didn't even have a lot of information at their site. They were affecting us. If we now put our own system in there, it's going to affect them. So when we designed it, we made sure that our animals were far enough away that it wasn't affecting them. Okay, I have a couple more slides. No one's fallen asleep yet.
Yeah.
And he missed all the good stuff. So, sorry. Induced AC corrosion is another big thing. There's three things which I'll get into on the next slide, which that we consider with power lines. The big one for this right now is corrosion. To get corrosion, we have a lovely formula which tells us what the AC coating holiday and whether or not there's enough voltage being picked up from the power line onto our pipe to cause corrosion. This is the formula. In the formula, so IAC is current density caused by power line, AC signal, at a coating holiday. The threshold, so if we're in the 30 to 100 amps per meter squared range, we could have corrosion. Okay, so that's an industry standard. In the formula, we measure the voltage, and that's right here. So power lines, they fluctuate. How much power is on the line, what the load is. We would take the peak. Right here, we got 1.2 volts. So 8 times 1.2 volt AC that is induced. This is measured. This is not theoretical. We divide that by the soil resistivity, pi, and the diameter of the coating flaw. Studies have proven that the worst case scenario for AC corrosion is based on a coating flaw of 1 square centimeter. Okay? So we already know what the worst case is for the coating to be affected. The other thing to take into consideration, we measured 1.2 volts, but when was that? I have to timestamp that, call the power company, which they'll never respond to me, and ask them, at this time, what percentage of your peak load were you at? Okay, they might have been only running at 50% capacity, which now means I need to take 1.2 volts and say, okay, we're going to multiply that by 2 to get 2.4 volts, because that would be the worst case scenario. Our coating diameter is the worst case scenario. Plug it into the formula, get our AC current density. If it's at one of the thresholds in our industry standard for causing corrosion, I have a problem. And I have to go mitigate it. If I don't, I'm like, okay, we did our test, we measured, we calculated, worst case scenario, I'm not going to see AC corrosion at this site. Perfect. And typically you don't see a lot of AC caused corrosion. It's very, very minimal, it's very rare, but it does occur. There's two other things that we consider with AC. Steady state situations. So during a steady state, we're actually going to model the power line. So if I have a pipeline and someone puts in a power line, they say, hey, we're putting in a 10 kV line right here. I'm like, great. Now I got to go hire a consultant who's going to use sophisticated modeling to go out there and measure the distances between ground, when the phases change angles, how far of a distance they are from a pipe, what grounding do they have, what shield wires do they have, when does our pipe and our power line deviate, when do they come together, when do they cross, when do the phases change, all of these, when does the soil change, all of these are what we call electrical discontinuities, and each time it changes, that's a specific set of variables that gets put into the model. Sophisticated computer modeling for each set of discontinuities. And then we model it. We model it for AC corrosion, so current densities. We model it for voltage induced onto our pipeline, because if our pipeline comes above ground at a valve and we have a worker present and he goes and touches the pipe, he's leaning on it, talking to his buddy, during steady state conditions, is that more than 15 volts AC? If it is, safety standards say that we can't be above 15 volts, because that's a shock hazard. Okay? That's the steady state. This is during normal operation of the power line. If we are, we have to mitigate it. How do we mitigate? We mitigate it by grounding our pipe using what metal? What metal? Copper. ground, what do I have to do to it?
Cathodic.
Cathodically protect it. Or my steel pipe's going to corrode preferentially to my copper. So I introduce a bunch of stuff. So I mitigate, I ground the pipe, and that will get rid of AC voltage. So I don't have 15 volts on my pipe. So if someone touches it during a normal sunny day, someone touches the pipe. The second scenario is fault conditions. If there is what happened to our tall metallic structure? Lightning. If a lightning strikes the power line, what happens to the lightning? Most big power lines have shield cables that capture the lightning. Where does it go?
To the ground.
Goes in the ground using copper. And where is that ground? Oh, is this a meter away from my pipeline? Oh, really? That has to be modeled. What is the anticipated fault condition? Okay. How much voltage are we talking about? What kind of ground are you using? What is the distance from my pipeline? What is the solar resistivity for that to arc to my pipeline? Okay, because that can now cause two problems. It can cause instant corrosion. It can also cause a safety concern if somebody's leaning up against the pipe. Oh, it's a lightning storm. I'm fine. Not if we don't have mitigation for that here. Not fine, because you know. So there's that. Any questions? AC, perfect. Okay, I think I have 2 more slides. They're just general. You can ask me questions if you want. So here's a tank. We're going to design a CP system to protect the underside of that tank, which is in contact with soil. It's going to corrode. What kind of corrosion rate do you think? Pretty minimal. Why? Because the tank is like sitting on the soil. It doesn't get any moisture in the soil. You know, there's not a lot of oxygen getting into there. Okay, when they build pads for these, typically it's crushed rock, drains really well, there's no moisture there. But guess what? They still corrode, and they corrode bad because when you fill a tank with oil, it puts weight, the oil puts a weight on the bottom plate, pushes into the soil, there's still moisture in there, it's still corrosive, and you can have corrosion. So we have to go design a system. Last slide. This is one type of system you could design. Okay? What's important when designing a CP under tank system is looking at what's under the tank. Okay? What's under the tank is going to be covered in corrosion. That's the soil, the electrolytes, in contact with the soil body, or with the steel tank wall. It is almost impossible to change a foundation design. Why? Because, the civil engineer stuck in their ways, they designed it, like, hey, this is what we're doing. And then, oh yeah, we got to put cathodic protection on that. So, hey, cathodic protection engineer, get over here. You need some animals over here. We're like, well, you feel like some cases they'll have a dielectric liner that's like a foot, 30 centimeters away from the tank wall. And you're like, we can't put anodes into a foot. Okay, if we do, we have that same 60 degrees in each direction from our anode, but our spacing is now only like 30 centimeters. So guess what? When I do a design, the spacing of the anode, now it's like a foot and a half between the anodes. We need like so much anode material just to protect. So we always go back and be like, hey, we need more space. Can you lower the membrane, get more crushed rock, and whatever, just make this larger so that we can put our anodes down here and have more separation separation distance from the anode to the bottom of the tank. One example I had, we designed a system, they wouldn't budge on this. We put in our anode, and they were literally like, I think they were 20 centimeters away from the bottom of the tank. So you lay your anodes down, and now they got to come in with some crushed rock, shovel it on, shovel by shovel, compact it, and get that 20 centimeters. Well, guess what happens is
The tank
do
compacted.
you want it? No. Before that, Ed's the laborer now, and he's got a shovel.
He's hitting all the. Oh my gosh. Oh, he doesn't put 20 centimeters.
Well, he might not put 20 centimeters. He might trip over the anode cable.
He might cut the anode.
He might get tired and his boss turns it around and he's like, I don't want to shovel all this on here. I'm going to drive over here and dump a bunch of rock on it. So this is the only time, one example, the only time I know of where the anode actually touched the bottom of the tank. And what happens in that scenario? Your tank bottom is now connected with your anode in the circuit, and it becomes anodic. So you have to turn the system off. This is not going to work. All right, I think that's it. So you can do centric rings of anodes. You can actually, in the previous slide, this is where we had an existing tank that didn't have a system. We actually drilled underneath of the tank to put anodes in because there was no liner. So we could do that. All of this has to be designed as far as choosing the right anode, choosing the right layout, understanding the soil configuration, and sizing it all, making sure you have the right separation distances between your anode and the tank bottom, and how you do it. So that all goes into it. All right, that's all I got.